right? So we looked at the equation, the ith equation, and it's basically this ith equation works for every equation in this system of ODEs, I equals 2 up to n minus 1. And we unpacked that and we looked at what the ith row of P is. And then where we left off last time is we started working on the I equals 1 equation. Now the I equals 1 equation was different because when we discretized the second derivative, we found this term here, this u0, which I put in quotation marks because this term actually doesn't exist. And so what we're going to do, the main point of what we're going to do today, or at least start out with, is to use our boundary conditions to figure out what is this u0. Okay, so picking up where we left off last time with that, our boundary condition, in this case, our boundary condition that applies to this equation would be the left boundary condition. So you have minus the diffusivity of u times du dx, sorry, du1 dx is equal to q at the left boundary. Now, if you recall, what I was saying about that is that this q, this could be 0 or constant or a function of t, u1, u1, v1, w1, etc. Basically the first element in all of our state variable vectors. And this, because it's a minus, this is a flux to the right. Now what we want to do with this flux is we want to take it and we want to discretize the derivative in this flux term. So this flux term is approximately equal to negative du times the discretized derivative. And we're going to take a centered derivative again. So previously we'd done a centered derivative or about point xi, and now we're going to do a centered derivative about point x1. And so the centered first derivative about point x1 is u2 minus, again, this fake u0 over delta of x, and in this case, the delta is 2h. And so what we see is that this fake location I need to spell correctly today, fake location, which is x equals to a minus h. It appears in two places now. It appeared in our actual differential equation, and now we see it again. Oops. We see it again in our derivative. So let's take a look at the simplest example of how to use this, and that would be if QA equals to 0, so we have no flux boundary conditions. So in the case of no flux boundary conditions, where this is equal to 0, then you can simply solve for this fake term, u0, and that's just equal to u2, just by plugging the above equaling to 0. So if u0 equals to u2, then our equation for I equals 1 is du1 dt equals to the diffusivity times 2u2 minus 2u1 over h squared plus f1. And so the only thing that happened here, you still had this f, but the only thing that happened here is that now this u0 is equal to u2, so you combine those two to get 2u2. And so that's the simplest example of what you would do. And in that case, the first row of this matrix P would have a -2 in the first element, a 2 in the second element, and everything else is 0. Let's step it up just a little bit and make QA equal to some constant that's non-zero now. So in that case, u0, if I solve with the boundary conditions, u0 is equal to u2 plus 2h over the diffusivity times q at the left boundary A. So the difference between the previous example where it's no flux, and this example where it's constant flux, is that QA here is non-zero. So you can see that this non-zero constant is a more general case, right? So the no flux boundary condition is a special case in which QA equals 0, right? So it just eliminates this term. Okay, so what happens now if we plug this formulation for U0 into our differential equation at x equals a, then what you get is du1 dt is equal to our diffusivity, du, times u2 minus 2u1 plus u2 plus 2h over du times qa all over h squared plus f1, where f1 again is a function of all these, potentially all of these time and all the state variables. Okay, so you notice here, okay, so I didn't do this very clearly, but these terms here, these are our u0, right? So I just plugged in for u0 and we got these terms here. Okay, so now simplifying this, what you get is du1 dt is equal to our diffusivity times 2u2 minus 2u1 over h squared. So far what I've done is I've taken this second u2, I've combined it with the first one, just like we would do with no flux. But now this extra term here with a qa in it, I'm going to pull outside of this, of these square brackets. So then what you get is outside of the square brackets, you get a plus 2 qa over h plus f1. So now if you have a constant flux boundary condition with your constant flux being equal to this parameter qa, then this term q2 times qa over h appears in your first equation, your equation at x equals a. So let me go ahead and write that out. Specifically this here, this is your new term. And this new term accounts for constant flux. And it only appears in the I equals 1 equation. Because that's the only place where this constant flux is occurring at the boundary in that equation. And the other thing that you'll note about this is the first term in the square brackets. This looks the same as the no flux condition. Compare what's in the square brackets here to the analogous set of terms. Well, I didn't draw square brackets in this equation, but the round parentheses here, it's the same set of terms, right? And so when you have a constant flux, you get the same row for this transport matrix, but you get this extra term here in the equation. Okay, so in both cases, this first row of P is equal to 1 over h squared times -2, 2, 0, 0, etc. The rest are zeros. So in both the constant flux and the no flux boundary conditions, you get the same first row. Now, if this flux here, this QA, is not a constant, but it's a function of things, that can be generalized too. So we could, if we had wanted to, instead of saying constant flux, we could have said QA is a function of whatever we wanted there. So I'm not going to go over that particular scenario. So in all cases, this first row of P looks the same. You have a -2 in the first term, a 2 in the second term, and everything else is 0. Okay, so now we're going to look at the I equals n equation. And it's very similar to what we just talked about. There are a couple differences that we'll watch out for, and I'll point those out when we get there. So the I equals n equation is dun dt equals to the diffusivity of u times u n plus 1. And now that's the fake term, minus 2 un plus un minus 1 all over h squared plus fn, which is in general a function of time, our state variable u at x equals b, our state variable v at x equals b, any other state variables that are in the problem, all evaluated at the boundary b. Now, our boundary condition then is du times the first derivative, dun dx, is equal to qb. So that's the flux at the other boundary, right? And just like qa, this qb, this could be 0, constant, or some function of t, un, vn, wn, etc. Now, if you're paying attention, what you might have noticed is that I didn't put a minus sign here in front of the diffusivity on the left-hand side of the boundary condition equation. And that's because this now is the flux to the left. What we're looking at here is the flux to the left. And so it's not a negative sign. If we put a negative sign there, it would be a flux to the right. And then we would have to put a negative sign on the other side. Okay, so since this is still a first derivative, we want to discretize the first derivative. And so this becomes the diffusivity times a centered derivative centered about u sub n now. So we have un plus 1. Again, that's our fake term, minus un minus 1 all over 2h. That equals to qb. And therefore, we can solve this in general for un plus 1 being equal to un minus 1 plus 2h over diffusivity times qb. And with that in mind, we can plug this back into our differential equation. Our differential equation becomes dun dt is equal to the diffusivity times, square brackets, 2 un minus 1 minus 2 un over h squared plus 2 over h qb plus f sub n. So everything looks the same as it did before. You have this new term qb showing up in this boundary in the equation at x sub n. And you have just those two terms inside the square brackets representing the row of p. Okay, so that nth row of p then is equal to a bunch of zeros. And then, I forgot the 1 over h squared out front, right? So you need that 1 over h squared. That's part of the matrix P. And then you have a 2 and then a minus 2 finally, where that final element is the nth element, and the one before that is the n minus first or n minus 1th element. And also recalling that QB could be 0, constant, or function of all the stuff we've been talking about before. Okay, so these equations, they look the same, and it's just, you need to just be careful on the boundaries where what's in square brackets, you have to take those into account. And then the boundary conditions, they show up outside of the square brackets in a very particular way. Okay, so to recap, what do our equations look like? Our first boundary, our left boundary, you have just the two terms inside the square brackets. You have this new term, which is our boundary condition. In general, all the other equations in the middle, you have the 3 terms in the square brackets. You don't have a boundary condition. The final equation, you have, again, 2 terms in the square brackets and your right side boundary condition. And QA, QB could be 0, 0, constant, or function of t and state variables at boundaries. Okay, so the last thing that I want to say here about this is that, about QA and QB, is that they are positive if source, negative if sink. So for example, with the example of Bitcoin, which actually is the example we're going to look at just in a few minutes here, QA and QB, or QA in this case, will be positive because the left boundary, or the anterior pole, that's where the Bitcoin mRNA is. That's where Bitcoin protein is being produced. And so we're going to consider that a source of Bitcoin protein, in which case QA is positive. And we set the boundary conditions up specifically for that reason. If I scroll back up to my boundary condition for the left side, it had a minus in front of the flux. And so this is the flux to the right. So the flux to the right, if this is a source, is positive. So QA will be positive, and this flux to the right will be positive if you include the minus sign. And that's because, if I can draw this really quick, I don't have a whole lot of space here. But if I draw this over to the right, if you have a source at x equals 0, then your gradient in space will look like this. That's your source, so that's the highest point, which means the derivative at that point is negative. So you need a minus times a negative to give you a positive source. On the other hand, if you have a source at the other end, then your gradient will look like that, in which case the derivative at that end is positive. So scrolling down to that boundary condition, you have a positive derivative here. And so the convention of having a positive source makes sense. If I flip it around, and if you have like a sink at the end, draw that really quick. If you have a sink at the other boundary, then your gradient might look something like this. So you have a negative derivative. This will be negative. A sink will have a negative constant here, and so it'll match up. It makes sense that way. Okay, so that's why the boundary on the right, you write down the flux to the left, and the boundary on the left, you write down the flux to the right, just so the sources and sinks can have their conventional signs. Okay. All right, so that is what each one of these equations looks like individually. But what we want to do is we want to represent these in their matrix format. So the matrix format is going to look like this. So you have your derivative of your vector u dt is equal to our diffusivity times our matrix P times u plus 2 over h, our boundary condition QA, times this vector E1, which I'll explain in just a second, plus 2 over h times our boundary condition QB times a vector En plus our vector valued function f, which is all of our reactions and other things that are taking place in the system. And what do these vectors E1 and En look like? So these are elementary vectors. The elementary vector E1 is a vector, it's a column vector, but I'm going to draw it as a row vector first. It's a column vector with just a 1 in the first element and everything else is zeros. And then E sub n is an elementary vector where everything is zeros except for the final element, the nth element, and that's a 1. And the reason why we have these here is because if we're going to put all these things into matrix format, and QA, the QA term is only appearing in the first equation. So you need this vector here to show us that it's only appearing in the first equation. And then QB is only appearing in the nth equation. And so this is what our kind of our vector valued or matrix format equation will look like. And this is going to be important because when we do things programming in Matlab, this is what Matlab will see. We'll define a matrix P, we'll define a vector E1 and En, and then we'll put this into Matlab this way. And that's what Matlab will use to solve the differential equation. Last thing about this is that the matrix P looks like the following. So we did it row by row, but just what it looks like in total, you have the 1 over h squared out front, and then the matrix itself looks like you have a -2 in the first element of the first row, and then a 2, and then a bunch of zeros. The second row, you have a 1, a -2, and a 1, and then a bunch of zeros. The third row, you have a 0, a 1, a -2, and a 1, and then a bunch of zeros. The fourth row, again, it looks like a repeat of the first rows, except for everything is shifting over to the right. Finally, if we skip down to the final 2 rows, for the final 2 rows, let me draw the end brackets of the matrix so I know where I am. The final 2 rows, you have a -2 in the final element, a 2 before that, and then zeros before that. In the row above that, you have a 1, a -2, and a 1. So the pattern follows all the way down, where on the main diagonal of this matrix, you have -2s. -2, -2, -2 on the main diagonal, which includes the final 2 rows as well. And next to that, those -2s, you have a 1 on either side for almost all the rows, except for the final row and the first row, you have just the 2 next to it, next to the -2. Okay, so that's what the matrix P looks like. And we can write down some Matlab code to quickly put together this matrix P so we don't have to like type it out by hand, which would be incredibly tedious. And I'll show you that example in a second. Okay, so this is what our equation will look like. And we're going to write a function in Matlab to put that equation together. And then we're going to use ODE 45 or 15S or some other piece of the Matlab ODE suite to solve for it. The final thing I'm going to say before we're going to get to our example is the output of ODE 45 is going to be some matrix U, which looks like the following. So the first column of matrix U is what U is doing at point x equals a, or x1, over time. So the first element is U, evaluated at t1, comma, x1. The next element down is U, evaluated at t2, but it's still the same spatial point x1. Dot, dot, dot. And then the very bottom of the array, which is the output of ODE 45, will be U, evaluated at t final, comma, x1. The second column will be U2. So that's U at t1, x2, U at t2, x2, dot, 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 U at t final, comma, x2. And then you can extend these out to the final column of this array, UN, or corresponds to UN, which is U at t1, comma, xn, U at t2, comma, xn, etc., all the way down to the final element, which is U at t final, comma, xn. Right? So you can see that as you go across the columns, you're looking at increasing x. And as you go down the rows, you're looking at increasing t. Now I said that was the final thing I was going to say before we get into the example problem. But one thing that I didn't really cover is, and I started to cover it, I started to set up the problem like we were going to do this, but I haven't actually done it, is what do we do with these other state variables, right? Because all I've done is shown you u, but there's also, you could have a system of equations where you have state variable u, state variable v, state variable w. Like, what do those look like? And I'm not going to talk about those in class. The homework problem requires that the graduate students do that part, in which case, we can have a little talk among ourselves about what to do, how to generalize this to having more state variables than just the one. But the example we're going to do in class is on Bicoid. And in this example, we're only going to look at one state variable. So it becomes a little bit more complex to talk about. It's kind of easily generalizable if you think about it, but it becomes a little bit more complex to talk about. So we're going to leave it at that for now and just leave it with one state variable. And that will be the example we look at. Okay, so we got about 20 minutes left in class. And so I think we're going to do this example, and I think we're going to be done for today. Okay, so we're going to look at this simplified model of Bicoid that we looked at earlier, where you have, when we looked at it earlier, we were assuming steady state. We're not going to do that anymore, obviously, because we're going to treat this as a series of differential equations in time. And so before there was a 0 here, and when we non-dimensionalized it, there would be no coefficient in front of the second derivative, and then the coefficient in front of c was this Thiele modulus. Now, because you don't have a 0 here, you actually get a parameter popping up multiplying this first derivative, and that would be the timescale tau, right? So tau, in this case, because of the way we did the non-dimensionalization with the Thiele modulus popping up here, tau has to be defined as L squared over d, and that would be the timescale of diffusion. We could have redefined the way we non-dimensionalized this, and instead of having a Thiele modulus here, we could have had a 1. We would have had a lambda squared here, and then the tau would be different. It would be 1 over k, which is the degradation rate. But we didn't do it that way. We're going to stick with the Thiele modulus here. According to the boundary conditions, then the boundary conditions are the constant flux at the left boundary, and I think I put this -1 here. It's got to be a +1. No, it's actually correct. Usually I was writing the -1 over here, the minus on the left-hand side, and the plus on the right-hand side. But we're going to do it. It doesn't really matter which way we do it. And then no flux at the other boundary. Now we solved this analytically in class, and what we found is the steady state solution. At least we found that to be the hyperbolic cosine of phi times 1 minus x, all divided by phi times the hyperbolic sine of phi. So that's the solution that we're hoping we're going to find at steady state. If we run this simulation long enough and it gets to steady state, hopefully it'll match the analytical solution. Okay, so we're going to use Matlab to solve for the Bicoid concentration as a function of time and space. So before I, let you guys work on this by yourselves for about 5 to 10 minutes, let's go ahead and write down what this PDE will look like as a series of ODEs when we discretize it in space. So it's going to look like tau, the parameter tau, times dc dt equals to the matrix P times the vector c minus v squared c plus our constant flux boundary condition at the left side, 2 over h times E1. Actually, before I let you guys start working on the code yourselves, there are a few things that I need to show you about the code first before you're ready to go. So let's open up the code here. Okay, so hopefully everyone has had a chance to download these two files that I put on the Canvas website for Bicoid, both the script and the function. Okay, so the first thing that you need to do is you need to discretize x. So x is not a continuous variable, it's a vector. which takes on values from 0 to 1. And we're going to say we're going to take on n, capital N values. And the Matlab function that can do this for you is something called linspace. So it's a linearly spaced vector between 0 and 1 with n points. Our h, which is our delta x, we're going to just define it here as x2 minus x1. Okay, so what we need to do now is we need to define this transport matrix. And I think this might be the hardest part, because if you don't know how to do this, if you're not familiar with these kind of weird Matlab functions, then you'll never have seen this before and you won't know what to do. So to define our transport matrix P, the first thing we're going to do is we are going to define a vector, which I'm going to call E. And we're going to define this as a vector of ones. It's basically a column vector with endpoints and just a whole bunch of ones. And then we're going to say that P is equal to SP diags. This stands for a sparse matrix with diagonals. And we're going to say bracket, open square bracket, E minus 2 times E, n square bracket, and we're going to divide that by h squared. So this is like the foundation of our matrix, where we have a whole bunch of ones in one column. Next to that, we have a whole bunch of -2s. Next to that, we have a whole bunch of ones again. And of course, it's divided by h squared. So we're going to transform this matrix, which is this 3-column, really tall matrix of, I guess, 51 points. And we're going to transform that into a matrix where this is going to be spread out on the diagonals. And that's what SP diags does. Okay, so the first column here. Oh, so the next element, or the next input that we're going to put into this SP diags function is -1, 0, +1. What that does, what Matlab does with that is it says, okay, this first vector that you've given me, I'm going to put that on the -1st diagonal. That's the diagonal right below the main diagonal. This next one that you've given me, this next column, I'm going to put that on the 0th diagonal. That's the main diagonal. And this last column here, I'm going to put that on the first diagonal. That's the diagonal above the main diagonal. Still, we need to tell it how many rows and columns in our final matrix, because we can make this tri-diagonal matrix this way, but we could make it with a whole bunch of zeros at the end. Or we can make it tri-diagonal this way, and we can make after that a whole bunch of zeros below it. But we don't want that. We want it to be a square matrix with n rows and n columns. Okay, so when we run this, let's go ahead and run it actually first. I'm going to define n equals 51. I'm going to define my vector E. Oh, I need to define H as well. So I'm just going to run everything. Okay, and now I'm going to run this last command. And so now I've constructed my matrix P. So if I look at and everything was working, that I didn't throw an error by accident. Now our matrix P, if I look at it, let me just look at the first like 5 rows and 5 columns, because I want you to see what it looks like. And when I hit enter, it's going to be confusing. It's not going to actually show us a matrix, because this is what's known as a sparse matrix. A sparse matrix is one that has a whole bunch of zeros in it, which ours does, right? Everything off of the 3 main diagonals is a bunch of zeros. And so Matlab, because it's a sparse matrix, it stores it more efficiently in memory, and it can do computations with it a lot faster. So what we really want to do is we want to see what does the full version of that look like. And I'm only doing this to show you what this matrix looks like. And so we have our -2, 1, and of course h squared is there making this, instead of -2, it makes it -5,000, right? 1, -2, 1, etc., all the way down. Now remember, we didn't want a 1 here, we wanted a 2. So we have to fix that. So if I go back to the code here, after making this sparse matrix that has the structure that we want it to, I'm going to make the first row, second element, equal to twice what it was before. And the final row, next to last element, equal to twice what it was before. And I put an extra parenthesis. Okay, so if I make a comment, a bunch of comments here for you guys to follow along with. This first one is make a vector of ones. The second line is place -1, -2, 1 on the 3 diagonals. And the last one is to double these 2 elements. Okay, so that's the code that we're going to use to construct our matrix P. All right, our parameters. Our Thiele modulus will be 5. Remember, that's the Thiele modulus. That's a sweet spot that causes the bicoid gradient to decay perfectly to almost 0 at the end of the embryo. Tau, I'm going to say 60, and this will be 60, I think, seconds. So this will take like a time scale of about a minute for diffusion. Q, I'm just going to say it's equal to 1. I don't really care what it is at this point. It's just going to scale our bicoid gradient up and down. It doesn't really matter to me in this problem what that is. Our function handle will be the name of our function here. We're going to have it go for an hour, 60 minutes. Although that's weird that I put 60 seconds here and now I'm having 60 minutes here. I'm wondering if there's something that I messed up with that. I'll have to go back and look and see if this runs correctly or not. Okay, our initial condition will be just zeros everywhere. So just a whole bunch of zeros. We're going to assume that nothing is happening at the very beginning, and we're going to watch the bicoid gradient grow over time. And then we're going to call on ODE 15s. So F handle, comma, I was saying that I would let you guys do this, but I'm doing it all for you. Oh well, T span, initial conditions, open brackets for our options, which we're not going to say any options. And then we're going to give our extra parameters here, which I said over here in this function would be our Thiele modulus, our time scale, our constant flux, our matrix, transport matrix, and our delta X. Okay, so now everything else is filled out actually in this function. So now if I run this, it should work, except for I haven't defined my equations yet in the function. Okay, so this is almost gratuitous at this point to send you guys over to do this. But there's one line here that I want you guys to type in. And actually there's a second one you need to define what this is as well. And I'm going to let you guys have about 4 minutes to work on this. We're going to pause the recording. I'm going to turn off cameras and stuff, and I'm going to come back in about 4 minutes, and you guys can see how close you got to actually writing down the correct equation into your code. dc dt P times C plus 2 over H times Q, okay, times E1. Okay, yeah, minus phi squared times C over tau. Perfect. Okay, so what you see here is this is a matrix, and that's fine, right? This is a vector. This is a vector. That's okay. Matlab knows how to work with all of these things. And when this all works out, you get a vector, which is this long vector. It's like 51 points. And so you have 51 ODEs that Matlab is solving. Each one corresponds to a different position in space. And they're all coupled together by this matrix P, which makes one point in space affect another point in space, and that's fine. Okay, and that's what we have here. Now there's one piece missing from this code, and I'm wondering if anyone wants to say what they thought should go here. Okay, so you could put in 51 there. Perfect. How many of you had 51, if you don't mind volunteering? 51? Yes. Everyone says 51? Okay, that's correct. That is numerically correct. However, if I go back and I say, you know what, I need more points here, and I go back to my script and I say 101, at that point, now I also have to go back and fix this. A different way you could do it is you could say size P, comma 1. So your matrix P should be n rows by n columns. And so it can, the size of your system is already sort of embedded in one of the elements or inputs that you're putting into this function. And it doesn't have to be P, it could be C, because C should also have the same number of elements. So it doesn't matter either way. And actually in that same way, you don't actually have to say what H is. You don't have to pass H as a variable. We actually could have said, because the second row, first column of P should be a 1 over H squared. You could put that instead. And you can kind of extract H out of the matrix P as well. That feels a little bit more icky, so I'm not going to do that. We're going to pass h as a variable. Either way, you could do it though. All right, so now this should work. Everything is in place. I think this should work. We got 1 minute left, so hopefully it works. Let's go ahead and run it. Run the script. And we should get a bunch of figures. And we did. You guys can't see them because they're on my other screen, so I'll pull them down for you. Here we have the Bicoid gradient over time, and it's growing in time up and to the right. And it approaches a steady state of this really thick black curve, which if you see down here, that is our analytical solution that I plotted here in black. The code for black is K, and a line width of 2, so it's thicker than the other lines. You can see that they are actually all converging on our analytical solution. So we did it right. We did it right. The other weird thing about this, which I just noticed, as you could tell in the middle of my lecture. So here, this is what the Bicoid concentration at x equals 0.5 is, right? So this is the Bicoid concentration right here in the middle. And so you can see how it like starts off slow and then it grows really fast and then eventually reaches steady state, right? Starts off slow because Bicoid hasn't diffused there yet. And then it starts to grow really fast when the Bicoid gradient front diffuses out past that point, and then it reaches steady state at about 20 minutes. And what's weird about this, which I don't totally get, I don't totally understand, and maybe I should know and I just haven't thought about it well enough yet, is that, okay, so we're simulating this for 60 minutes, right? But it only took 1/3 of that time to reach steady state, at least in the, in the center of the embryo. But our tau, which is our time scale of diffusion, is 60 seconds. So from my perspective, usually I'm thinking like 3 times tau, or maybe even 5 times tau is how long it would take for this system to reach steady state. But it was actually 1/3 of tau, at least for it to reach steady state in the center of the embryo. So it's a little bit weird. I don't totally understand it. Maybe I should know this better. Like maybe this is one of those intuitions that you learn in transport in chemical engineering. And I've forgotten it because I haven't taught transport in a while. And I haven't really played with this system very much, even though I wrote this code. So I don't know, it might be something to think about and then revisit in the future in a later lecture.